Excuse me, ma'am. Nag-start na ka, ma'am?
Yes, nag-start na po. So, okay. So, again, last meeting, no, we talked about one of the reactions of carbene. We are currently using our laboratory time to finish our lecture discussion for carbene, so that on Friday you can simply have to study or finish with your problem sets now, so that you can be prepared for our exam, which will be on Monday or Tuesday. I will inform you whether it's Monday or Tuesday. Okay, but that will be for the major exams. So today we'll continue with our discussion. And by the way, as I have mentioned in the messenger note, you will have your laboratory activity in the lab. I will have to take that into consideration. You will be doing your face-to-face laboratory in the lab after the midterm exam or after your midterm break. I think it's 7, April 7 ba to 14. And after that, para dili alanganin, no, you have to prepare being near the city or the university. If you have a lot of major courses, no, for which you can perform your laboratory. So what is being allowed sa face-to-face setting actually is simply the laboratory setup. For all the lectures, we are still bound to do our kani-nani virtual. Okay. But for the lab, that is the only thing that's being allowed for us to do the face-to-face session. But in the next school year, yes, in the coming first SEM academic year, no, 2022 to 2023, then I think the university will be ready for us to do full-time face-to-face setting as a university. So right now it's just a simulation, but I prefer not to do your laboratory since we are preparing for the exam, which will be on Friday. We have our exam for the other chemistry courses, and for the major chem, you will be scheduled either Monday or Tuesday. If I'm not mistaken, it is on Tuesday. Okay, so let's go back to our. And remind me later, no, I haven't indicated the ID attendance. I don't know where are the others. You are 15 ba mo ata yung section, and usually the only people who participated in our lecture discussion is kanang 6 to 7. So I wonder what happened to the 8 no, kung maka-cope up pa ba na sila, kung nagtanaw ba sila sa ilahang ga-review ba sila sa mga video or self-study ba sila. I don't mind, no, you can actually read your textbook. Our main textbook is Solomon's. You can just follow that one. You can answer end chapter questions. It will be very good for you. You can actually pass, or even no, sa future ninyo nga mga exams or licensure exam, mo gina siya ang technique. You have to answer all the end chapter questions. Even sa general chemistry ninyo nga mga courses, no, if you are to study physical chemistry, inorganic chemistry, the general chemistry books would be a big help, no? 80% or 70% sa mga exams award will come out even from the general chemistry books, and you can actually answer. You can actually get a high score, no, if you can answer most of the problems, 80% at least. Sa end chapter questions, you can be sure nga perfect mo sa exam or get a high score. Okay, so I really hope that for most of you, no, since you are base chemistry, do not just watch the lecture notes or watch the reaction like you already know. You have to implement it. You have to really write all the compounds, the reactions, and you have to think, no, and how you have to really use your motor skills so you can apply what you have already learned. Okay, so let's go back to our lecture. It will be still on the reactions of alkenes. Again, there are too many reactions of alkenes, very important. Actually, alkenes is one of the starting materials, no, in the organic synthesis. You want to do synthesize other compounds. Usually chemistry starts with alkenes. So there are a lot of reactions of alkanes. You have learned that so far in the previous discussion. And this one is usually the addition of alkanes. And so you have to summarize that at the end of our chapter. Okay, so for today, we'll continue. We'll continue with our discussion. So we have learned, just know what are the reagents. For every reaction, you have to identify, of course, your starting materials. And importantly also is you have to determine the reagents. Know what are the reagents that's being used. And what is the purpose of that reagent? What is the environment? Is it acidic? Is it in basic medium? If the reaction is made in aqueous, no? Or is the reaction made in organic solvent? For example, here, the reaction of carbene is always made in organic solvent. Even if you have your base, which is an alkoxide, is made in organic solvent. And sometimes you don't see, for example, this one is the source of CCl2. You can see it, but know that this one is the source of CCl2 from the previous reaction here. Okay, so even if the katong actual reactant, dili nimo siya initially makita with the reagent, but just know that that will be the source of your electrophile for which the alkene will add to your reagent. Okay, else. And then like this one also, it can be your source of carbene, just don't see it. This one, the CH2, the dot is having a complex with the zinc, which is a Lewis acid. So it cannot be seen that this one is your source of that's H2, your carbene, and this is like a carbenoid. Okay, so that was the last discussion. We will now proceed with another kind of reaction with alkene, which is the 1,2 dihydroxylation. And in this kind of addition reaction, it is in the syn. Okay, so alkane undergo a number of reactions in which carbon-carbon double bond is oxidized. So we begin to ask, when a double bond carbon is being oxidized, unsa day iyang product? Product actually is having a hydroxy group attached to your carbon. So there is a 1,2 dihydroxylation. So from the word hydroxylation, you get your hydroxyl group attached to your carbon. And if you have your double bond carbon 1,2, then 2 hydroxyl group OH is being added to the double bond. So this is actually the product of the oxidation of your double bond. You get a lot of oxygen. That's one of the indicators when you have the oxidation process. So the reagent that we use here is the Osmium Tetroxide. We use to synthesize this to get our 1,2 diols. So the hydroxylation is simply get your diols, alcohols, the OH, no, and vicinal diols, meaning they are on adjacent to each other, vicinal to each other, or like the glycols. And another agent aside from osmium tetroxide, we use our potassium permanganate. It's also an oxidation reagent. Remember your Chem 16, no? This one is a very strong oxidizing agent. And with this, using the potassium permanganate is prone to cleaving the diol through further oxidation. So with osmium tetroxide, actually get your 1,2 diols, okay? And if you still further use another strong potassium permanganate, it actually cleaves the diol to further oxidation. And we'll see that later once by further oxidized states of the alcohols. Okay, so here what you can see is you have your osmium tetroxide in an organic solvent. This time organic solvent is pyridine. And some pyridine. Pyridine is a cyclic, is an aromatic compound with a nitrogen in it, and can check later on the structure, but it's a ring with, it's like a benzene, but one of the carbon is substituted with nitrogen. Okay, so our agents here is osmium tetroxide, and then we have a little base or a source of proton here, you have your sodium bisulfate in water, so aqueous na ikaduha. And what will be recovered in this kind of reaction is the hydroxylation of this double bond. You get your OH. So in this case, we start with propene. You actually get your 1, 2, 3. You have your propane, carbon 1, carbon 2, diol. So 1, 2 propane diol. So the common name for this is propylene glycol. Okay, so you can also use our KMnO4 if we don't use the osmium tetroxide. In KMnO4 is an ionic salt, right? So it has to be performed in aqueous solution. Okay. So you have here, can have this one in the basic medium and in water, cold one, because it's very reactive. We have to minimize the heat evolved in the process. So we have to make this reaction cold. Okay. So you have your ethene here and you have your double bond. Your product here is the OH. Actually gets your ethylene glycol here. You add 1, 2 ethane diol. So if not osmium tetroxide, you get your KMnO4. So the mechanism for the formation of the 1, 2 diol by osmium tetroxide, it actually involves a cyclic intermediate. So what is that cyclic intermediate? This one. So you have your double bond, and then you have your osmium tetroxide. The osmium tetroxide, there's actually osmium, let me see. Have to see on the unsa ni siyang periodic table. Okay, osmium is part of the transition metal, same column with iron. Okay, and row 656. Okay, if you look at the share. Okay, you have here your osmium. This is your transition metals. You have your osmium here. Okay, so this one is Lewis acid, no, and it accommodates all the electrons of the oxygen. And so you will notice in the structure. Okay, it's capable. So since na siya sa row 6, no, it's actually capable of more than the octet. So ang katurang usual atoms rather that follows the octet katong naa sa second row. But beyond the second row, because they have vacant orbitals, no, they have the d levels, which can accommodate actually there are 5 or hybrid or not hybrid, 5 forget the term, 5 orbitals in the d sub level. No, what you will get actually can have more than the octet. So it can accommodate 2, 4. You can see here 2, 4, 6, 8, 10, 12, 14, 16 electrons here in the structure. Of course, oxygen will have 2, 4, 6, no, 2 and 2, 4, 6, 8, 2 unshared electrons for oxygen. Okay, so this one, of course, you have to remember osmium is one of the exemptions of octet because osmium is in the 6th row. No, it will have the, I think also F gun in the orbital. Osmium will have the F orbital. So there's a lot of vacant orbitals for osmium to accept electrons from the oxygen. So anyway, you have your osmium tetroxide here as our agent, no, to do a cyclic intermediate before we get our product. So what will happen? Here what we get is that your oxygen will be bound to carbon here, losing the electrons from the pi electrons here. So you'll lose your pi bond when the osmate ester, the cyclic compound, is being formed with osmium. So you have 1, 2, 3, 5-membered ring for the cyclic compound with osmium. You call this one as osmate ester, and we use a source of our proton. We actually get our OH. And what happens is that you have your OH osmium is being reduced in the process. You see here, there's a lot of double bonds osmium, and the process of reducing your osmium, see carbon double bond actually is being oxidized. So whenever you have a substance that's being oxidized, always have to remember that another substance is being reduced. It will be a redox process. If one substance is being oxidized, another substance will be reduced. So here, osmium causes this to be oxidized. So actually, that osmium tetroxide is an oxidizing agent, and by itself, since it's an oxidizing agent, it is reduced. So instead of having osmium double bond O, na OH na lang siya. So this one is a reduced form of the double bond O. The OH is a reduced form of the double bond O. Okay, so anyway, so this one is what you will see in the mechanism. An intermediate cyclic ring is obtained when we get a 1,2-diol in the process of reacting with osmium tetroxide. So after the formation of the cyclic intermediate, of course, it's in this one is cleaved, and the oxygen metal bonds takes place without altering the stereochemistry. So here you can see that this one is being added on the same side. So what you actually obtained here is the same hydroxylation. You have a same side OH, listen all to each other. Okay, so here you have another example. You have an cyclopentene. You have osmium tetroxide as our agent at a very low, temperature, normal temperature, standard temperature, 25 degrees Celsius, and the presence of organic solvent. We always have to have a solvent now whenever you have our reaction. Without a solvent, it's almost impossible to do the reaction unless it will take time. Solid. Okay, so you have here solvent pyridine, and so what happened is you have your osmate ester, and in the presence of sodium bisulfate, and this one is aqueous. This is inorganic. So what happened is that you get your OH. This is syn to each other, the same side. So you actually get a cis-1,2-cyclopentane diol. And you can see here, this one is a meso compound. You can look at center, there is a plane of symmetry. This one is a meso compound, and even if this one is a chiral center, but there is a plane of symmetry, this one is a meso, this one does not rotate the plane polarized light. So just a note for the reaction, osmium tetroxide is highly toxic, volatile, and very expensive. No, it's the transition metal, pinakaubos. It's very expensive. Pag mag-abot na gani atong transition metals, gani the usage of transition metals katong na nasa group 5, row 5, row 6, even in the row 3, no? Expensive din na siya kaayo, platinum, palladium, expensive na. So how much more, let's look at here. How much more pag kani titanium, vanadium, chromium, iron, cobalt, nickel, these are important elements no in most industrial processes. Copper is expensive din na siya. Pag-abot mo sa 5th row, you have silver and you have your cadmium. How much is gold? Si gold na diri sa 6, no? It's very expensive. So osmium is ka-rows yan ni gold. No? So pag-abot diri platinum is in the row 6 and the hafnium, thallium. Okay, you have your mercury. It's very expensive already. So osmium is hard to mine. Osmium, it's very expensive. Okay, what else? So it's highly toxic, volatile. So it's volatile. So when it's volatile, you have to do it under the hood, of course. For these reasons, methods have been developed that permit osmium tetroxide to be used catalytically in conjunction with a co-oxidant. So we normally don't use the organic chemists because it's very expensive and it's very toxic and volatile. No? They just use a very small percentage of the osmium tetroxide, and then they will use a co-oxidant to oxidize the process in order to proceed with the dihydroxylation step. So they will only use a very small amount of osmium tetroxide. And while the stoichiometric amount of co-oxidized co-oxidant rather, reoxidizes the osmium tetroxide as it is used in each cycle. So you noticed here, kani, di ba, na-reduce man si osmium tetroxide in the process. Pag magamit ang mga chemists of another co-oxidant aside anemia in the process of kani sa maka-oxidize ng si osmium tetroxide pa ani. If there is another co-oxidant, para ma-recover si osmium tetroxide, very expensive man, very volatile, i-reoxidize nila. So reduced form ani is i-reoxidize nila balik diriya. So you'll get your osmium tetroxides para ma-recover, no? Kay mahal ka. Okay, so they just use as a stoichiometric amount of the co-oxidant to reoxidize osmium tetroxide. That is the purpose of the co-oxidant. As it is used in each cycle. So allowing oxidation of the alkene to continue until all has been converted. Okay, so maski pag gamay lang amount ang ilahang gamiton para maka-oxidize sila kang alkene to have this. So you produce this one, and for example, wala na siya na completely oxidized, kay gamay lang amount of osmium. If you have your co-oxidant, kani siya ma-return back, i-reoxidize ni siya paingon diriya. So you get again your another this, and pag another cycle of this to oxidize this one, you get this one, ma-reduce ni siya, and so you have your co-oxidants to reoxidize this one to this. So this one also oxidizes again this until ma-complete, mahurot ni siya to how many cycles to obtain your 1,2 diol. Okay, so technique na siya para ma-optimize, no, ang reagent, which is very expensive. So sometimes N-methyl morpholine N oxide is one of the most commonly used co-oxidant with catalytic osmium oxide. So you can look into the structure here. This is also an aromatic compound. So anyway, later we'll be reaching the aromatic compounds in the next chapters. Only we can reach that one. So this is the common use co-oxidants. So here is an example of the osmium tetroxide, which is present or used in a very small amount, 0.2% lang of the overall relative to this one. And you have your co-oxidants. Whenever you have your NMO or N-morpholine, is it morpholine? Methyl morpholine Di-N oxide, methyl morpholine N oxide. This is not aromatic. You have here, so this is the co-oxidant. What will happen is that a small amount of this, you get a catalytic reaction. You have a reaction rather to form your dihydroxide here. So you see you have a ring there, but we will focus only the double bond. So even if unsa na siya ka-large na structure, you have your osmium tetroxide, you just only target the double bond here. So what you get is dihydroxyl 1,2 diol here. Okay, so as I mentioned earlier, even if in the start, no, first cycle, for instance, wala pa siya niabot to 95% yield. In the process of converting this to here, you get this one. So let's say 10% pa lang ang na-produce na OH here, 1,2 diol. So kani si NMO will reoxidize the reduced osmium tetroxide here para mabalik anemia. Okay, and then second cycle, for instance, it will convert this into another diol, so you get 20% yield, and then recycle again the reduced osmium tetroxide here to para mabalik ani, and then you get another until you get a very high yield to 95% greater than. Okay, that's how this whole reaction takes place in the laboratory. So question, explain the following facts. Treating Z2-butene, Z2-butene with osmium tetroxide in pyridine, and then in water gives a diol that is optically inactive and cannot be resolved. Okay. Then I say optically inactive, you already have an idea, no? You have 2-butene, even if you have 2-diol, whenever you get a meso compound, even if it is a chiral compound, there is a chiral center, it will always be a meso compound, just like katong kaganina, this one. Kani. Here, you have a chiral center here. You have your hydrogen OH, this group, and this group, Okay, so there are four kinds of groups attached to your carbon. This is chiral, this is also chiral. But since you get a plane of symmetry, the right is a mirror image of the left, no? And this one actually is a meso compound. Whenever you get a plane of symmetry, a meso compound, and a meso compound does not rotate a plane polarized light. So you couldn't resolve, even if you have a chiral center, you couldn't resolve that one. So it becomes inoctinium. So it's just like that one. So you expect your product here to be a meso compound. Of course, you get your 2-butene with osmium tetroxide. You get 2-butene, which is 2,3 rather. Can you just look at the structure here? You get here is, you have your E. Okay, and anong E man na? You have your Z. You have your Z here. Salvos. So what you get actually in the process for an E, you have your hydroxyl, OH, so 2,3. And what will happen, katong sa hydroxylation nato, this is for E, trans, no? What will happen is that you get a pair of enantiomers. Katong trans, remember? You'll have your OH added here, and you have your OH. So you have, okay, how do you write your CH3? CH3 oriented towards you and the hydrogen oriented away from you. CH3 or oriented dito. Okay, broken. Kani siya. This is if this is, for example, kaning sa plane, no, of the computer or laptop or phone. And the CH3 is oriented away from you, trans yan, and CH3 is oriented towards you. So this is E, trans. Okay, so what happens is, kung since siya, mo ni mahitabo na you will redraw this one, the OH. You will redraw, kaya you have here the trans man. I-redraw nimo ang imuhang carbon here because you will actually get a chiral center, no? So you will draw para ma-determine nato unsa nga product nga itong obtain here. So what will we get here is that you have your, if diri mo find ang si osmium diri nga side, what you get actually is your OH diri nga side. Okay, OH. So if the side katong osmate ester na, if the osmate ester diri nga side mo bind, you will have a cyclic ring here, and following the addition of sodium bisulfate and water, and break ang bond sa osmate ester, you get your OH. So diri nga side, sin man siya. So what will happen if the OH is added here? Ma-push down sila, kani sila, but you always have to remember nga kani CH3 is oriented towards you, the hydrogen is oriented towards you, and CH3 is oriented away from you. Okay, so you have this first product here. And then what you will have is that you can check on the stoichiometry of this. So an alternative way of adding your osmium is the ring aside. So si osmate ester will form a ring here, the ring aside. Okay, and so you will have your OS, and then carbon O, and then OS, and then of course you have your S here. So once it is being cleaved, you get your OH diri nga side, and ma-push na siya, of course, paingon dito sa H3. Tanawa ang drawing is oriented towards you, dark, and hydrogen is oriented away from you. Si hydrogen is oriented, kaning line is oriented towards you. CH3 is oriented away from you. Okay, and then you look at, there are two kinds of products that's being formed here, and then you look at the stereochemistry of each carbon. Okay, so you can determine what is the stereochemistry of this carbon. Hydrogen is away from you. Let's call on Mary J. Per. What is this? Is this R or this is S? First one of the arrow. You can prioritize. No? So hydrogen is already oriented away from you. It's broken. So this is already like 3 well. You have your OH, this group, and this group. So is this S or is this R? Unsa man? Okay. Unsa may kuan ani niya? You have your group here, 2 groups, right? You have your 1, 2, and 3. Si hydrogen is walay labot. It should be oriented away from you. So, sa first priority ni mo ani Japer, nakita ba? So, nakita ko screen. Okay, so you have your CH3. And you have here, you get your product, this one. So Mary Japer, what is the stoichiometry of this kanina carbon? Carbon 1, 2, carbon 2. Anyone? Hoy, ay tao. Abay tao. So may mo volunteer.
R, ma'am.
Okay, so you have 1, you have your priority 1, and then this is 2, and then this is 3. So paana, right? To the right. All right, so this is R. What about kaning number 2? You have your OH, you have this, you have your CH3, and hydrogen is oriented towards you. So di na ta magbalin, no? So kung kaning hydrogen is oriented towards you, dapat katanaw mo sa likod ani nga plane, kaning tulo dito mo sa likod. Pero pwede na ta mag-label kanina lang, i-assume na lang nato nga hydrogen is towards you. Kung sa itong makuha ani, baliktaran nato later. Okay, so your priority is, of course, first priority is OH. Second is this group. Second is this. So, unsa man na? This is S, right? S or R? To the left. Pa S man, 1, 2, 3, but baliktad man, sa baliktaran nato si S, sa baliktad ni S, it's still R, right? So this is RR. So let's look at this one. Yellow. Klaro ba? Si yellow, you have OH, CH3. Ano ba na sila doon? So your priorities, we have number 1, number 2, number 3. Okay, so 1, 2, 3. So S or R? Counterclockwise or clockwise?
Counterclockwise.
Okay, counterclockwise. So what is the configuration? It will be
S.
S. And this one, you have COH is oriented towards you. We'll use yellow. So you have OH, you have CH3, you have this. Okay, tanaw na to si yellow. Priority is, of course, number 1, COH, number 2 ni, number 3 si CH3. So 1, 2, 3. Ana. So unsa man na, counter or clockwise?
Clockwise.
So what is that? It is RS or R?
R,
This
ma'am.
is R. So unsay final configuration ani? Is it R?
S.
Okay, kay R man na siya and hydrogen is towards you man, i-convert pa nato na siya. Kay katanaw ta nga si hydrogen na towards ato. Dapat katanaw ta sa likod. So baliktaron nato. So this is actually an S. So tanaw nato this RR and SS, they are actually, the S is the mirror image of R, the S is the mirror image of R. This is actually called enantiomers. Okay? So when you have kani from your E-butene, the trans-butene, okay, you always have to, let's see if naabay. Asan na din ito? Okay. So you have here, you actually get a pair of enantiomers. And para dili maglibog, you'll have kani, redraw ninyo kung para di mo maglibog, you'll have your that, then you have your carbon, and then you have kani, you have your CH3, you have your hydrogen here, and carbon,